Okay, a quick overview of the board we're going to be using in the mill. This is a Smoothieboard V2 Prime with a TMC 2590 stepper drivers on it, which means it has these external FETs driving the motors instead of an internal type driver. This is good up to, I believe, 4.5 amps. I'm going to be running it at 4.3 on an XYZ. We have 6 end stop connectors here for high and low, or min and max, I mean. And then there's a probe input, which gives you anywhere between 3 and 45 volts, depending on your jumper setting. And it's a comparator-driven probe, so it's very repeatable. Next, we have a 5-volt regulator on board, and that is a 3 amp at 5 volt, so it gives you quite a bit of power. You can run output here off of this header. And then here we have a 3.3 volt on board. And these are all protected as well. There's a GPIO here, these Gadgeteer headers. Each one of these has a 3.3, a 5 volt, a ground, and 7 GPIO that are different various functions depending on which header you're using. Some have SPI, some have I2C, and some are analog or PWM. So you have to go through the list, and there is documented on the wiki the full list of every one of those pins. All right, down here we have the status LEDs. It gives you the VFET, the motor power in, whether you have 3 volt, and then some status LEDs which tell you functions and things that are going wrong or right. Here is the FET in. These 2 connectors give the power for the MOSFETs, and if you were to use this here, this would be the bed output for like a 3D printer. It's a dual FET, which gives you a higher current draw. These here are your normal quote-unquote FETs. They're just single FETs, so you would have 2 hot ends, 2 fans, and then next to that is there's 2 small high side FETs here, which are intended to drive solid-state relays. Over on the side here we have 3 thermistor inputs, give you measurements from standard thermistors. You get the reset button, 5 volt out, mass storage device button here. Basically, you push this button, your board becomes a mass storage device. It looks like a flash drive, and then you can eject it. It goes right back to being a smoothie board again. Onboard thermistor for the board. We have some flash. We got the Ethernet and 10100 Ethernet, SD with proper SDIO, USB with also USB host. The USB host does not function in our firmware. It is just a hardware wired thing right now. It's just there. Debug UART. This is a standard UART for SmoothieWare. You can hook up FTDI or similar type board to it to debug. That is essential when you're first setting up your initial setup. You want to have that there because that is the only way to get error messages if you have a configuration problem. So that needs to be connected. All right, now on the bottom, we have a heatsink area, which currently I'm not testing the heatsink on it. I'm going to test without it and run it at 4.3 amps just to see how hot the board gets, see how things are properly handled, and then later I'm probably going to put a fan or a heatsink on it. There's also TVS diodes on every one of the motors outputs, so those are protected from reverse EMI. All the FETs have diodes on them to protect them from the inductive kick so they can drive inductive loads. Here is a high side FET which is on these 4 FETs here. This is actually a high side which can shut off the power to those FETs in case there's a failure where one of those is stuck on. You can shut it off here in emergency too. Aside from that, there's also the real-time clock battery, which we don't have the part installed, but it does function. So if you were to throw that on there, it will function. We may do that in the future, but currently we're not. All right, that's the standard, what we're going to be looking at. And now to figure out how to wire it. Now, to choose how I'm going to set up this board. Now, my plan is I'm going to be using 3 motors, the X, Y, and Z. I'm going to be using the motor input. I'm going to be using the onboard 5 volt, which I'm going to be using this output here to drive the Raspberry Pi and touchscreen off of. I will be using these this FET here to drive the solenoid, which drives my mist. I will have the spindle and then the vacuum dust extraction on these 2 small FETs here. And I'm going to have 1 single thermistor on here just as a debug. It's an ambient. I can plug it on the board and test temperatures and such. I'm going to configure that. I'm going to have X and Y end stops as well as one probe. And since there's 3 different ways to choose 5 volt on this board, you can have 5 volt in, you can have 5 volt in via the USB, or you can use the onboard 5 volt regulator. Now, all these are run through ideal diodes. So in theory, there's protections, there's no backfeed, but there's also a way on here through jumpers. Now this jumper here will disable the USB via the MT9700 chip. If you jumper this, if you bridge this JP15, that will turn off the USB power in at the chip here that's on the other side of this board. Now up here, JP17 is a 2-bar connector. So there's actually 2 bars there you have to scratch off. Now, if you scratch that off, that cuts USB power completely at the USB. That won't even come to the board if you cut it there. Now that's what I did on the board that's on my machine. I actually cut JP17 completely, so I have no USB power because I'm using a Raspberry Pi, and there tends to be issues when you're feeding USB power from the Raspberry Pi to things, and also, sharing the 5 volt out. So I'm basically powering the Raspberry Pi off of this. I don't want a loop coming back around and putting more power in and, causing potential issues. So I completely separate the smoothie from this, so it won't turn on with this power. It needs motor power to turn on. So the motor power will turn on the 5 volt regulator, which turns on the 3.3 and turns on everything else. It turns on the Raspberry Pi, and that's about it. So mostly that's all I'm going to have connected onto here. But you can see from the board, there is actually quite a few different jumpers. Some of them are like the USB and the probe. So the probe is kind of interesting. It actually goes from 3 volts all the way through 45, I believe, volts, essentially 40 volts. So some people who are using inductive probes wanted these high voltage levels to be able to shift it. It goes through a comparator, so it's always going to switch at the exact same time. It's always going to switch perfectly, regardless of whether you're putting 3 volts to it or 40 volts to it. It's going to switch at that same point. So if you use 40 volts, your rise time is going to be a lot faster, and therefore your responsiveness should be faster. I mean, in theory, in electrical theory. In testing, I haven't done the testing completely yet, but I am getting very repeatable probings on things using these. I've been using it on a 3D printer for quite some time. But back to what I was talking about is that these jumpers, if you are using 3 volts, you want, your standard, if you're using a BL Touch or just a probe switch or whatever, you just want it normal. Now, if you want to run 5 to 24 volts, you need to cut one of the jumpers. And then if you want to run up to 40 volts, you need to cut another one of the jumpers. And that's basically just a level shifting. So I have that all set up, or that's all set up in there. It actually needs its own wiki page just to explain that. These other jumpers here, we got the end stop voltages. You can set, whether you want 5 or 3.3. You can also cut it out and disable the end stops if you'd like. And then USB cut, we already talked about. That cuts the USB. Then on the top, there is actually one right here. This, if you bridge it, will actually disable the 5 volt regulator. So if you don't want your 5 volt regulator to turn on at all, the onboard, you can just jumper that and it should shut it off and disable it completely. So you could use a different regulator and not rely on the 5 volt onboard if you wanted to do such a thing. I believe that's all the jumpers that are relevant right now, but more to come.